Good morning, students. Welcome back to
Sir,
our new course, Advanced Calculus and Numerical Methods. The course code is 18MAT21. So let's start. So before going to deliver this particular course, I will try to explain the course objectives. So we are conducting this course in our semester 2, and we have 5 hours in a week. As usual, internal marks are 40 and external marks are 60. The main objectives of this course is we are going to introduce vector calculus, differential equations of higher order, both partial and ordinary differential equations. And we are going to learn, here we are introducing numerical methods. So there are various methods which we need to know it. Till now we learned how to solve the problems analytically. So we should know how computers are going to be understood. That is the reason we have to be learn numerical methods. These are playing very important role nowadays. That is one important topic what we are learning in this particular course. So coming to the syllabus, how they categorize, it is struck. Yeah. So as usual, we have 5 modules. So module 1 is all about vector calculus. We are going to introduce both vector differentiation and integration. And one fortunate thing is that here almost the same syllabus is going to be delivered by physics teacher also. They have the same concepts like Green-Stokes, Gauss divergence theorem, and their problems also will be there as well as here. So anyway, we'll change our sequence of delivering the modules. In that case, we may not be in trouble. I think they are starting with the module 1. So we'll start with module 2, differential equations of higher order. As you learned already, differential equations of first order, like exact methods and linear methods, and Bernoulli equations, how to reduce to linear forms, all those we learn. Here we are going to learn about higher order linear differential equations, and we will introduce some Legendre causes equations. We can reduce non-homogeneous to homogeneous, and we can handle those problems. And in module 3, we will introduce partial differential equations. Till then, we are not covered. That is the reason. We'll start with formation of partial differential equations and how to get the solutions for those homogeneous as well as non-homogeneous, these PDEs. And there are certain applications in the partial differential equations like heat and wave equations that we'll discuss in module 3. And in module 4, we'll introduce about the sequence and series, which is also very important method to solve our differential equations. Here, we should know how the sequences and series are going to be applied to solve the differential equations, as well as when we are telling about the series, definitely it should converge or diverge. So we should know that whether the given series is converging or diverging with the help of certain tests like D'Alembert ratio test or causes test and all. We are going to discuss all those, and we'll introduce some more important special functions to solve our differential equations, so like Bessel and Legendre functions in this module 4. So this is completely new to you. And finally, I told you that numerical methods is one of the important topic in this particular module and very easy also. These are we are introducing because of the computation things are nowadays very easy to access it. So we are introducing few methods here, and in your higher semesters, again in third semester, we are going to do some more numerical methods, advanced numerical methods. Here, whatever you are learning, there will continue with those methods. Okay. And if you see the textbooks, we need to refer that was prescribed by the university, VT University, is B.S. Gravel, higher engineering mathematics, and Erwin Kreyszig, which was advanced engineering mathematics. So these two has to be followed, but as you know, we most of the time we used to follow local author textbooks like KSC, because those people are used to involved to prepare your question papers and all. So it's better to, they are the experts here in this local area. So almost 90%, 99% students are following these local author textbooks like KSC or DSC to get your good score also. We will also tell you that please go through that, but it doesn't mean that you should not follow these textbooks. These are actually prescribed textbooks you should follow who are preparing for GATE examination and who want some more work. Definitely you can follow this. I will provide the soft copies of these two if I have with me. Okay. All right. So, and how we are going to deliver this particular course is that we'll start with module 2 because module 1 is already have some classes with the physics. So we'll start with module 2 and module 3. Actually, it was not taken by me. We have CCI, Chief Course Coordinator. Her name is Dr. Shweta. So she will decide which module has to be start and how to go ahead further. So as per CCI's requirements, means their suggestions, we wish to deliver our course. Here, module 2, we'll start with the module 2 and module 3, and then directly we'll jump into the module 5, numerical methods. Then we'll finish module 4, series. And finally, we'll come to the module 1, vector calculus. So this will be the sequence what we are going to follow. Okay. Is it clear till then?
Yes, sir.
Yeah. So now, without waiting to something, let's start with the module 2. Topics are here all about differential equations of higher order. So I will introduce today. So what is meaning of this higher order differential equations, and we should learn this. Okay, we should learn them. That is also a very important question. Of course, this is very important definition and basic definition. Everybody knows that it contains derivatives. Differential equation should be having derivatives. Here if you see dy by dt in first equation, that is the derivative. In second equation, we have two derivatives, dy by dx, d square by dx square. Okay. So this having y is here the dependent variable, and the remaining variables t and x are independent variables. You see here, in first equation, depend on t, y is changing. In second equation, depend on x, y is changing. So here in both the equations, t and x are independent variables, and y is your dependent variable. So when you can say these equations are linear equations, let me check with you how many of people are identified the linear equation here. Have you identified, is there any linear equation here? Linear differential equation?
First one, sir, dy by dt plus 5y is equal to 3d.
Very good. So that we know already, it was there in our first semester, this type of dy by dx plus py is equal to q form, which is called first order linear differential equation. So on what base we can say that it is a linear? Because its degree is 1. For the derivative dy by dt, the power is 1, so that it is a linear differential equation. If power is more than 1, then it will be becomes non-linear. That's what we learn. Is it correct or not?
Yes, sir.
Yes. So what about the second equation? What is the order and degree for the second equation?
2 and 1.
Very good. Order is 2, and for that order, highest order degree is 1. Very good. So let me check with other derivative. What is the degree? The same equation, second equation. Other derivative means dy by dx, first order.
1 and 1.
1 only, right? D square y by dx square, degree is what for that?
Yes, sir.
1.
1. So each and every derivative, so derivatives are involved, not only the first order, second order, maybe higher order derivatives will be involved. For all those derivatives, if degree is 1, then we can say that those are linear differential equations. So here in this case, our first equation, this one, 1 minute. So first one having the same degree, okay. So if you see here, for this it is 1. For this and this, I'm just writing the powers. So what is their power for all these derivatives? 1, 1, 1, right? So in that case, we can call it as these are linear differential equations. Whether it may be the first order or it may be the higher order. Here higher order means it is a second order. So all these are linear differential equations. Linear differential equations. And one more terminology here. This derivatives should not multiply with the dependent variable. Suppose here dy by dt is there. If it is multiplied with the dependent variable y or y square or y power 10, then that will become a non-linear differential equation. In this case also same thing. Suppose in place of 7, I have some y cube. In place of d square y by dx square, here I may have some y square, something like this. So these derivatives, whatever derivatives are involved in your differential equation, those derivatives should not multiply with the dependent variable y. That is also one more condition. If you want to call it as the given differential equations, ordinary differential equations, you want to call it as a linear differential equations. What are the conditions? What is the first one? The dependent variable and its derivatives should occur only the first degree. Here dependent variable means y and its derivatives. And its derivative means dy by dx, d square by dx square. Dependent variable y and its derivatives all occurs first degree. So if you see the degrees are 1. So in that case, I can call it as linear differential equation. Here also same thing. So dependent variable y and its derivatives dy by dx. So for all these derivatives are degree is 1. And one more condition is the dependent variable should not multiply with its derivative, any derivative, whether it may be first or second order or higher order. So that should not happen. So in both the equations, that is not happen. So these are linear differential equations. Suppose some derivative is multiplied with y, dependent variable, then I can call it as it's a non-linear differential equation. That we will discuss later how to handle this non-linear to linear. That part we'll discuss later. Is it clear? Have you understood linear
Yes,
differential
sir.
equation? Okay, good. So here I introduced 3 definitions. One is differential equation which contains derivatives. So next one is actually we already know that when you can call it as an ordinary differential equation, when you can call it as a partial differential equation. There are 2 types of differential equations are there here. One is ODE, here I returned, and the second one is PDE, partial differential equations. So ODE means it contains only one independent variable. If you see here, t is only one independent variable in first equation. Here, x is only one independent variable in second equation. So when you have only one independent variable, we can call it as an ordinary differential equation. If more than one independent variable is involved, then we can call it as partial differential equation. Okay, so those are definitions. Here we are just considering only ordinary in this particular module, ordinary differential equations. In that also, we're starting with linear differential equations. So linear differential equations are the equations which have derivatives occurs only in the first degree and they are not multiplied with dependent variable. That you should remember. Is it clear? Every derivative, the degree should be 1. So now, for your understanding, I will take nth order differential equation. Okay. Before going to discuss, I want to discuss about some applications here. See, as you know, differential equations, all these are serves as a mathematical models for many real world problems, isn't it? It arises in many areas in our science and technology. They plays very important role, especially in engineering when things are changing. Everywhere when there is a change, definitely these differential equations will occur. So like by taking some examples in COVID situation, we see how cases are changing. We can predict the things also. And in population change or heat moves, even these spring vibrates, all these are, of course, belongs to mechanical people, radioactivity material decays or growth, all these examples. I listed out here few examples like fluid dynamics, electronics and circuit design, all those. Okay. So everywhere equations will be involved, but the problem is here, as a mathematician, I know the equations, I can solve it. But as an engineer, you should know how to model the equation with your physical interpretations. That we are going to learn from your second year, second semester itself, because that time all your theoretical, all this theory part, core subjects will be introduced to you. So even some subjects will be introduced in second year, first sem itself. So what they will do when they are explaining some topic, they used to explain, describe all this physical interpretation, and they will prepare the equations. Okay, so that time you should be very careful how that equation is preparing. Once equation is prepared wellly, nicely established with their boundary conditions and initial conditions, then our time is now to solve those differential equations. Here, what we are learning the methods how to solve this differential equation. We are not teaching you how these differential equations are framing from physical phenomena. Okay, that please see this change. Okay, applications are there, not many applications. As I mentioned, you just go back, few applications are there here in our syllabus. One is electrical circuits, another one is see here, LCR circuits will be there, and some oscillation problems are there. Only 2 applications are there. These are not enough, that what I'm telling. Okay, so you have to learn so many things. Those we can continue in our maybe okay, something cancelled. Maybe in the next semester we are going to learn all those, how to prepare, how to frame these differential equations. Right. So let's start with our topics. As I mentioned, I'm going to introduce nth order linear differential equation. By seeing that, don't panic yourself with that equation. Okay, I will explain everything here. Like we have a naught d power n y by dx to the power of n plus a1 d to the power of n minus 1 y by dx to the power of n plus and so on. You may have like an minus 1 into dy by dx plus an into y is equal to x. If you see this equation, just I extended few terms here. So first linear differential equation, first order is dy by dx plus py is equal to q. Have you remembered this?
Yes, sir.
Have you remembered this? So now second order may be d square y by dx square sum p dy by dx plus qy is equal to sum r. Means I'm just added one more term. So if you see in those terms, the derivatives are there, their degree is 1. If you see, those degrees are 1. P and Q are constants here. With constant variables, initially we will take it. So here in this case also, constants are maybe functions of x, usually we will take it. P and Q are functions of x are constant. But for our understanding, I am going with constants now. And here in this case, what I done, first we have dependent variable, then derivative started first order. Here it may be started second order derivative, then like it will continue nth order derivative. So if you see all these derivatives, what will be the degree? Degree is 1. What about a naught, a1, a2 up to an? All those are
Constant, sir.
constants. I am assuming as a constant. Maybe functions, no problem. But functions of x only. Because on other side, I returned capital X. That means here I'm going to take it functions of x, f of x. So this a naught to an, all may be the constants or functions of x alone. That you should remember. You should not get y there. If you get y, it will become non-linear differential equation. Do you understood? You should not get y there in place of these constants. Is it clear?
Yes, sir.
LDE definition is clear.
Yes, sir.
LDE definition is this is higher order linear differential equation. A1 to an, all these are constants, either constants or functions of x alone. Now, maybe many people will be, by seeing this equation, you may be a little bit panic. That is the reason we are going to introduce one operator that is called differential operator. Differential operator. Okay. So what it means, I have, wherever I have d by dx, I am going to replace with capital D. Okay. In place of d by dx, I am replacing with capital D. Suppose if I have d square by dx square, then I am going to replace with capital D square. This D stands for your differential operator. So like I can continue, suppose I have d power n, d power n by dx to the power of n, that I can write it up as d power n. Okay. So if I replace this with this equation, what I'm going to get it? Tell me anybody. A naught.
A naught to the power of d power
D
of
power
n.
n.
D power n into y is there, right? This y,
Yes, sir.
isn't it? So y
Plus
plus
a1
a1 d power
d to the power of
n
n minus
minus
1 into y
y plus and
plus
so on.
so on plus
Yes.
a
Next,
to the power of n minus 1
yeah, a power n minus 1 into
d to the power of
dy, n minus 1
d1
into d into
d into
y,
y
plus
plus
finally
a
a
to
power n into
n
y, which is equal to
equal
x.
x.
Are you able to substitute this d operator in this general equation? This is our general equation, nth order equation. Are you able to substitute with this differential operator?
Yes, sir.
Okay.
Yes, sir.
So what we observe in each and every term, y is common. Have you observed? Y is common, right? Each and every
Yes,
term
sir.
y is common. So
Yes, sir.
I can take y term is there, so I can take y as a common. Each and every term y is exist, right? So that I can take it as a common. What I will do, I can write a naught d power n plus a1 d power n minus 1 plus a2 d power n minus 2 plus and so on an minus 1 into d plus an. In all the terms, y is common, which is equal to x. Is it clear?
Yes, sir.
Yes, sir.
Yes. Now, suppose I have this equation ax square plus bx plus c. So, what it represents equal to some 0. What it represents? It's a quadratic equation, right? So, we can call it as it's a polynomial of order 2, isn't it? We are representing this as some f of x is equal to ax square plus bx plus c. I have something like f of x is equal to some ax cube plus bx square plus cx plus d, something like that. So, it is polynomial in x. That's why I'm representing this with some function f of x. Is it clear? Now, this is also, if you are observed, it is polynomial in d. So, I can represent this with f of d, this whole equation which is in polynomial in d. In place of x, what I returned here, ad square plus bd plus c, something like this. So polynomial in d, I can take some representation f of d into y is equal to x. Can I take it?
Yes, sir.
Okay. So this is very, very important equation. What we are now coming to the conclusion, some simplest symbolic form representation of our higher order differential equation is f of d into y, which is equal to x. Okay, this is very, very important representation of your higher order differential equation. Suppose if x is equal to 0, then this will be homogeneous differential equation. If x is not equal to 0, okay, not equal to 0, then we can call it as non-homogeneous differential equation. You already know this. In our previous class also we discussed about, isn't it? Even linear equations, while solving our system of linear equations also we discussed about this. Have you remembered? So here f of d into y is equal to x. If x is equal to 0, which is a homogeneous differential equation, and if x is not equal to 0, then this will be non-homogeneous differential equation. Correct?
Yes, sir.
Yes, sir.
Have you understood till then?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So now we have to get the solutions for this differential equations. Okay? How to solve these differential equations? To solve these differential equations, let me start with the homogeneous form. Okay? Homogeneous form means I don't want to take x first, f of d into y, which is equal to 0 form. Okay? So this I want to consider. To solve my differential equation, I am just assuming that there is no x, so I am just considering homogeneous differential equation. Okay? So now, if it is, because it's a polynomial here, it has roots for this, isn't it? I can solve this polynomial. I will get n roots for that. Something like I may have like roots y1, y2 up to yn roots, I will get it. If I solve it, this particular equation, f of d is equal to 0, solving for y, okay, because it's a polynomial in d, so solving for d, we will get d values, all these values. Let us assume instead of m1, m2, m3, d is equal to, instead of y1, y2, y3, m1, m2, like mn equations are there. isn't it? What is our equation? F of d into y is equal to x. Now I'm taking homogeneous equation. If I solve f of d is equal to 0, I will get the roots. All those roots are, we have n roots. I am assuming f of d is nth order polynomial. Nth order polynomial. Is it clear? Okay.
Yes,
How
sir.
many roots I
Yes,
will
sir.
get it?
N number of roots, sir.
N number of roots I will get. So now the question is that this solution of the differential equation. So when I substituted this in this equation, it has to be satisfied because these are the roots, right? So whenever I wrote to solve the solutions, when I'm solving f of d into y equal to 0 for this homogeneous equation, taking f of d is equal to 0, this equation is called auxiliary equation. Auxiliary equation. Without disturbing your original differential equation, to get your roots, to get these roots, we are separately writing the equation as f of d is equal to 0 and we are solving. So with this auxiliary equation, we are getting roots. Okay. So depend on these roots, the solutions of this differential equation, we are going to write it up. It depends on completely roots. What type of roots are there? Based on that, we have the solutions. Okay. So what I will do it, there are certain rules. Those rules are based on these roots. If all these rules, M1, M2, Mn, all these roots are real and distinct, real and distinct. So that time the solution will be, we have m roots, n roots are there, n roots are there, are there. So all roots are real and distinct. Then the solution will be, for this differential equation, we have to include arbitrary constants for all these n roots. So C1 with exponential, we are going to get the solutions. C1 m1x plus C2 e power m2x plus C3 e power m3x plus and so on, Cn e power mnx. So all roots are real and distinct. We will write those roots separately by adding with each and every solution with arbitrary constants C1, C2, C3 up to Cn, because all are independent and we have to write it up separately. And we may have doubt this, how we got this solution. Okay, isn't it? How you got this solution for this? Hello, are you following?
Yes, sir.
Yeah. Anybody have doubt how you got these n roots? Why should take it this as in this form only? What is your first order differential equation? dy by dx plus py is equal to q, isn't it? So in place of this, as I said, let me take other side, q is not there, that will be 0. Okay, then it will becomes homogeneous linear equation. So in place of this capital D, I am representing dy minus py, which is equal to 0. So what we have here, d minus p into y is equal to 0. Isn't it? I'm solving that equation. First equation. Right?
Sir,
So
dy
d
plus
minus
py, sir.
Sir,
Dy plus
yeah,
py.
sir,
plus
can you write a little more bigger? Like it is
yeah,
unclear.
actually today there is a little bit problem with this writing pad. That is the reason it is not comfortably
Yes,
written
sir.
anyway.
That's why I'm
Yeah, yeah.
telling you, just write bigger, sir. Then it will be more
Okay.
distinct.
Yeah,
Thank you.
definitely, definitely. Okay, I will do the same thing. So what I'm telling, we have first order differential equation. I will take with one example so that it will be easy for you. Suppose I have something like simple one, I will take it. D cube y by dx cube. Can I start with the squares?
Yes, sir.
Okay. D square y by dx square plus 5 dy by dx plus 6y. I think this is okay, right? Everybody knows. Equal to 0. Right? This is the differential equation. What is your initial step? Replace this with capital D's to make it simple form. So d square plus 5d plus 6. Everywhere y will be, you can take it as a common, which is equal to 0. Here, what is this d stands for? D stands for d by dx. So I hope you understood how I returned from here to here. I'm taking one example to explain to you. Is it clear?
Yes, sir.
Yeah. Yeah. Now this particular equation we are calling as this whole thing is a differential equation. Up to this f of d, this we are calling as f of d into y, which is equal to 0. This up to this it is f of d. So for f of d we are solving separately. D square plus 5d plus 6, which is equal to 0. This is your f of d. What will be the roots for this? Everybody knows, right? What are the roots? 2 comma 3, right? Minus 2 comma minus 3. Is it correct?
Yes, sir.
Yes, sir. Yes, sir.
Yes or no? Right?
Yes, sir. Yes, sir.
So based on this, we are going to write the solution for the differential equation. Okay? Here two roots are there. These two roots are real and distinct. These two roots are real and distinct. When these two roots are real and distinct, and we have complement, we used to call it as solution for the differential equation. In general, solution will be for second order, it will be C1 Y1 plus C2 Y2. Y1 and Y2 are the two solutions. We have to take its linear combination. Okay? Y1 and Y2 because it's a second order. Suppose I have nth order, then Y will be equals to C1 Y1 plus C2 Y2 up to Cn Yn. Now, in this case, the solutions always comes in this linear differential equations are exponential form. So C1 in place of Y1, I'm taking exponential form e power m1x means 1 root minus 2x plus C2 exponential form e power minus 3x. I will write the general equation so that you will understood. Suppose I have m1, m2 up to mn. These are the roots. Okay. Then the solution for the differential equation is our differential equation f of d into y is equal to 0 form. For this solution is y is equals to c1 e power m1x plus c2 e power m2x plus and so on cn, because n roots will be there, e power mnx. I am assuming initially m1, m2 all are real and distinct. Distinct means different roots. When roots are real and different, I can take their linear combinations. All these are solutions. So let me check with this whether it is correct or not, whether our solutions are correct or not. So see here, what solution we got here? E power, first solution, y1 is equals to e power minus 2x, we got it. Okay, I have to substitute this in this equation. What is y2? 2 times for this. This is y. Okay, solution. Let us assume it is a solution. One solution for this equation. D square y by dx square means 2 times, you tell me. Yes, please. What do you got? This is y. Y is your function. E power minus 2x we got. 2 roots we got, means 2 solutions we have for this differential equation. You take first one. Okay. First solution is e power minus 2x. I am assuming, I am telling that it is a solution. If it is a solution, it has to be satisfied this equation.
Yes, sir.
Okay. So in place of y, I can substitute e power minus 2x in place of y. Here dy by dx means derivative for y. Derivative for e power minus 2x is minus 2
2x into
e
power
power
of h.
minus 2x. So 5 into this one. One more time derivative means this
Minus
is 4
4
into e power
into power of
minus 2x.
minus 2x.
Yes. So now this is plus 4, this is minus 10, this is plus 6. Correct?
Yes, sir.
So it is going to be satisfied, isn't it?
Yes, sir.
So that is the reason e power minus 2x is one solution for the differential equation. Do you agree or not?
Yes,
Similarly, I have one more solution. I can check it. E power minus 3x is also solution for the differential equation. Both are independently solutions. Therefore, their combination also becomes a solution. It's a combination. Now, this is also going to be a solution. Of course, C1 and C2 are the arbitrary constants. Okay, those are arbitrary constants. With the help of some particular solutions, we can get it. Forget about the arbitrary constant at present. Okay, to find out your based on your initial conditions, you can get these arbitrary constant values, and their combinations also becomes a solution. That is the reason we are making our solution, general solution, y is equal to C1 y1 plus C2 y2 for 2 roots. When it goes to the n roots, what I have to do? I have to continue the same procedure. That what I am writing here. Suppose I have n roots like m1, m2 up to mn, then I have to write the linear combination as the solution like y is equal to C1 e power m1x plus C2 e power m2x plus C3 e power m3x and so on. Is it clear?
Yes, sir.
Okay, it depends on the roots, whether the roots are real and distinct, roots are real and equal maybe. Okay, if roots are equal, how many roots are equal? It depends on that. Okay, based on that, we are going to write the solutions. So all those we will discuss in our next class. So actually, they asked us to take only 45 minutes, and we have to take the attendance. Then we have to give some time to you to attend the next class. Next class is at 10 o'clock. Okay? Is it clear?
Yes,
Yeah.
yes, sir.
So
Yes, sir.
what I will do, yeah, I will take your attendance now, and I will first of all will try to discuss